Before we get started on the notes over definite integrals and the fundamental theorem of calculus, I thought it might be good to give sort of a broad overview of this class to try to explain why I think today's lecture is the most important of all of the ones that we're going to see in the class, and also to try to justify why I think the fundamental theorem of calculus is appropriately named. So let's look at this framework. So we've studied differentiation so far, and we've looked a little bit at integration. Today we're going to sort of complete our picture of integration in some sense. So throughout, let's let P of t denote the position of a particle at time t, and V of t will denote its velocity. So we've already sort of considered this situation before, and we've seen that the velocity function is just the instantaneous rate of change in the position. So if I graph the position function as a function of time, and I want to talk about the velocity, then the velocity at time t is just going to be the slope of this tangent line here at time t. So at any particular time, I can just take the derivative, and that will show me the velocity or the instantaneous rate of change in whatever quantity we're measuring. So if I wanted to know how many miles per hour we're going, or the instantaneous rate of change in the position, then I would just compute this derivative. So if you know P of t, you can use the derivative to get V of t. But what if we wanted to go in the opposite direction? So what if we know the velocity, so we know the speedometer readings, but we want to know the position, or how much the position has changed over some interval of time? So for this, let's consider this example for a second. So let's say that my x-axis is measured in hours, so it measures the time t that we've been going on, let's say a road trip, and the y-axis is going to represent the velocity at time t. So this would just be what's on the speedometer at each time. So for the first 2 hours of this trip, we were traveling at 30 miles per hour, and then it looks like after time 2, we moved up to 60 miles per hour. So for the last hour of the trip, we were going at 60 miles per hour. So let's say that this is the graph of V of t, and I want to know the position that we've covered. So I want to know how far we've gotten by time t. So maybe let's first focus on just the first hour. So we'll look at this time. In the first hour, we were going 30 miles per hour for 1 hour. So we should have traveled 30 miles in total. But notice that if I take 30 miles per hour and multiply by 1 hour, in terms of the units, miles per hour times hours, those units should end up canceling out and giving us the units miles. So this would give us 30 miles if I just multiplied this height times this width. In other words, the area of this block is going to give me the distance that we've traveled. Or if you'd like, we can phrase it as a change in position. So the position that we've gotten to by time t, or well, in this case by time 1, would be 30 miles away from where we started. And similarly, the area of this second block would be 30 miles. That's also how far we would travel in that second hour. So the distance that we've traveled by time 2 would be 60 miles in total, because the area for each of those initial those initial hours would be 30 miles each. And then notice that for the last hour, we were traveling 60 miles per hour for 1 hour. So if you go 60 miles per hour for 1 hour, that would give you an area here of 60 miles. And that means that by time 3, we've made it 120 miles in total. So that would give us the position that we've made it to at time 3. So to summarize, the position at time 1 would just be the total area that's amassed under this velocity curve by time 1. And the position at time 2 would be the area by time 2, and the position at time 3 would be the area by time 3, and so on. Right? So if you want the position, but I only give you the velocity function, then you want the area under that velocity function. That would have the units measured in miles, or whatever position units you're using, and that will allow you to compute the position given the velocity. So let me make this a little fancier for a second. So let's write the integral from a to b of f of x to denote the area under f of x between the initial point x equals a and the final point x equals b. Then the position at time t would just be the area from the starting time to whatever time t you're interested in under this velocity curve. So this is just sort of a fancy way of writing what I just said earlier, which is that if you want the distance that you've covered by time t, then you would just take the area that you've got under this curve by time t. So what we get is that the position can be obtained just by integrating this velocity function from your starting point, which is time 0, up to whatever time you're interested in, time t. So to go from p of t to v of t, we would differentiate like we did at the beginning of this class, but now we can see that to go from the velocity to the position function, we would just integrate. In other words, we would go in the opposite direction. We would take an antiderivative. So this sort of completes the picture that we've been building so far in this class. For the first half of this class, we were focused on building up the derivative. So we saw how to go from a position to a velocity function. And now that we've seen integration, we know how to reverse this process and to go from a velocity function over to an initial function p of t, or a position function. So the fundamental theorem of calculus is what codifies this entire diagram. So it gives us a complete understanding of how to go from a quantity to a rate of change in that quantity, or vice versa. So it completes our picture of the relationship between a quantity and how quickly that quantity is changing. And because that can be phrased in such abstract terms, you can see why this has universal application in any sort of quantitative science or engineering. And this is in fact why calculus was invented in the first place.